Hi everybody, my name is Alexander Gard-Murray. I'm the Executive Director of Passive House, Massachusetts, and I'm so excited to welcome you to this evening's talk on residential ventilation measurement with Dr. Iain Walker. I'm going to introduce our esteemed speaker in just a moment, but first, before I begin, I just want to mention that this event, like all our events, is brought to you by the sponsors of MassSave and their Passive House and All-Electric Homes Training and Workforce Development Program, which offers, as longtime fans of the show know, robust incentives for passive house construction that I encourage you strongly to take advantage of early and often. They got single-family incentives, and then more germane to tonight's talk, multifamily incentives, which start at $3,750 a unit for multifamily residential development, plus adders on top of that. And so if you're starting a passive house project in the state, you should get on this. And you can email multifhr@icf.com to get started. If you have questions, you can email passivehousetrainingma@icf.com, or you can go to phmass.org and talk to us, because we would also love to help you with navigating these incentives and anything else related to passive house. So thank you again to MassSave for their support. Tonight's speaker is Dr. Iain Walker. I had to print out, normally I just memorize people's credentials. This time I had to print it out because there are so many things. He is the leader. I'll say them quickly. I'll say about half the things that I could say. He's the leader of the residential buildings team at Lawrence Berkeley National Lab. He's a fellow of ASHRAE. He's a deputy department head for the whole building systems department of the Building Industrial Energy Systems Division at DOE, the leader of the DOE National Laboratory Indoor Air Quality Team. I'm just going to say words. ASHRAE, ASTM, RESNET, IEC, IEA. It doesn't matter if it's got letters in it, he's involved.
I like letters.
Yeah.
Very good.
Yeah, he's pro letters, and as we're going to see tonight, pro numbers as well. And so we're so excited to have, I've been pitching this as Dr. Ventilation, but we're so excited to have Dr. Iain Walker to come present to us on his areas of expertise. Let's give a big PH Mass round of applause for Dr. Walker.
Thank you, Alexander. Here we go. So yeah, who's measured the residential ventilation airflow in this room, by the way? Anybody? A few of you? Almost all of you. Fantastic. That's a good start. Because one of the things that doesn't happen in the world of buildings is measuring ventilation airflows. I would go wider and say, you know, we're in a very big building tonight, big commercial building, lots and lots of ducts, lots of air inlets and outlets, and they didn't get measured well either. But our job is to change that, right? So I'm going to talk hopefully not too long. I want to only talk for 30 minutes. If I go over 30 minutes, jump up and down, point fingers at me, just to give sort of some background and introduction to this sort of topic. And then I think we'll just better do like a Q&A because I could just blather all night about ventilation, which would be painful for everybody. All right, and hello, maybe not. Well, if I could do the next slide.
You do now. There we go. You got it now.
Victims of technology. So a lot of this, I'm only telling you what you already know, right? I just wanted to throw some things out there just for context for the rest of the evening. And I wanted to start out with something that I've been on the ASHRAE 62.2 standard for a long, long time, chaired it for many years, seen this many ups and downs and this many foibles. And something I wanted to point out was there's a lot of things where in the world of passive house things are a bit different. And I would argue that when a lot of codes and standards refer to ASHRAE 62.2, they refer to old versions. 2010 is popular. But what they don't tell you is that 2010 only works for a leaky building. And the thing I wrote in red is almost certainly true for a passive house. It's not a leaky building. Sneakily hidden in there for reasons I won't go into right now, but sufficient beer later we might actually talk about it. There was this hidden assumption that every home, every dwelling, would get 2 CFM per 100 square foot of floor area for free all the time. And the rationale was, because homes are leaky. And if you go and do some calculations, the sort of leakiness levels we're talking about depend a bit on how big the house is and so on. And here we're talking about natural infiltration driven by wind, stack effects, you need to be around, I don't know, 4.5 to 8 ACH 50. Those are not passive houses, right? There are other requirements for passive house about precision and accuracy when we're testing. I just put those bullets at the bottom there. Those are just things to bear in mind when I talk about some of the test methods we're going to talk about today. So a little bit of history. Why did we ever start to measure ventilation rates? So even more important, why do we put in systems that might need measuring? So some of this goes back to the 1970s oil crisis. This wasn't just in the US, this was all over Europe as well. People started thinking about, my energy bill's too big, I need to have a better house, or just generally a better building. But I'm here to talk about houses today. So we started airtighting and insulating, and you're passive house people, you know all about this, right? But almost instantaneously, people find out that if I build an airtight box and put human beings in it, bad things happen. And really bad things happened. And so pretty soon, 1979, IEA Annex 5 was formed because we were finding all these bad problems and we had to better understand what the heck is going on with, it was first called the Air Infiltration Center, AIC. Now it's the Air Infiltration and Ventilation Center. We'll talk about the ventilation tonight. But it was to understand building air leakage, how do we measure it, what does it mean, what do ventilation systems have to do? They talked about very, very complex tracer gas measurements, things that I would never do it again either. But you know, there's still an ASTM test method for that if you want. But that was just to do R&D really. It wasn't really, a lot of the things they were doing back then were not super practical from an engineering or a design perspective. And we followed that up with actually trying to create some requirements. Once we sort of better understood what was going on in buildings, sort of in the late 80s, early 90s, we started to have these requirements for mechanically ventilating dwellings. And yes, we had been mechanically ventilating buildings for a long time by then. ASHRAE is the organization here in the US, and they'd like to be international, and they're getting there, that talks a lot about this. It was the old standard 6289, was based on a lot of history. And by the way, the ventilation levels have gone up and down a lot over the years. And we cut off a new part. We call it 62.2 for residential only in roughly 2003. And you know, 6289 had these requirements. I put them in italics here. And a lot of this was really based on commercial systems, not necessarily on things you would do in a home. Like it's based on ideas like, well, I've got this long straight duct for about 100 feet, so I can put a flow grid in it. And the manufacturer of the flow grid says I need 20 to 40 upstream diameters of straight pipe, and I can do it. That never happens in a house, right? So those original test methods and measurement techniques were okay if done right in a large commercial duct system, but not so great in residential. And then all sorts of alphabet soup organizations, some of which I've been a member of and some of which I haven't. And you know, Alexander was pointing out, I love some alphabet soup. The HVAC measurement industry had standardized test methods. Again, almost none of them were useful in homes, right? They all use techniques and approaches that are very, very difficult. They all still exist today. They're used in commercial buildings all the time. They use things like flow hoods with big openings and duct traverses and things like that. But as I'll talk about in a few minutes, that doesn't work well in residential applications for a host of reasonable reasons. And moving closer to the present day, we've actually been able to develop methods that are much, much more applicable to the residential setting in terms of airflow, what sort of glow measurements are we talking about. And it's true for both, not just ventilation systems, but all the airflows associated with things like heating and cooling systems that are forced air also. There's this thing called RESNET, which is an organization that tells us how we might rate homes for energy use. I'm sure you're all familiar with it. It has a whole standard RESNET 380 that some of you in the room have worked on, and I have worked on a lot too, that sort of pulled together all sorts of test methods, including things like how to measure how leaky buildings are, how to measure all their airflows, and so on. So that's sort of how we got to where we are. Innovation has happened, and I mentioned that we had this problem trying to apply what works in a commercial building to residential. It just didn't work. Back in the 1990s, people started innovating, and some of the innovations were pretty straightforward, but worked surprisingly well. Probably some of you have seen this device. Other companies are available, by the way. I have to say that. This is just from the Energy Conservatory. Basically, it's a box with a calibrated hole, right? Or multiple holes. It's super simple. It's easy to use. We were able to do this because pressure sensing got easy and cheap. Until the 1990s, that wasn't true, right? A good pressure sensor was thousands of dollars. You had to calibrate it very, very carefully using sophisticated laboratory techniques, which, you know, a university researcher, a PhD student like me would do, but you couldn't expect anybody else in the world to do that sort of nonsense. That was just crazy. But we got better pressure sensors. It enabled this idea of, oh, if we can measure pressure well, we can come up with simplified diagnostics. Now, this is okay if I'm measuring, say, an exhaust fan in a bathroom, but as my note there says, if you try to do supply flows with this, forget about it, right? It really, really doesn't work. And if you have a multi-branch system, you stick this on one branch, stops the flow in that branch, you measure very low numbers, and the flow goes up everywhere else. It's just a nightmare, basically, from that perspective. Adding all this airflow resistance, which is what it's based on, doesn't help you unless you have very simple systems. And great for those simple systems, we should understand it doesn't work always. So what do we do next for innovation? We started to think about actively doing things. So we wanted to compensate for that the extra flow resistance that a flow meter has. This is one of our first LBL prototypes. We have a little powered fan there, which is a built-in flow meter. The cardboard box is the flow hood, if you will. You stick that over whatever it is you want to measure. And so we've got an integrated flow meter. We're overcoming those insertion losses. So now I can go and measure various branches on a ventilation or HVAC system and probably do okay, right? We got incredibly more complicated and ridiculous as time went on. And thankfully, we didn't have to do that for that long because manufacturers of test equipment came along and said, yeah, that's a mess. We can't legitimately put that in the hands of contractors, right? And you know what? Now you can get something that doesn't look like that, but it works the same, right? It's got a little fan in it, it's calibrated, it lets you measure all sorts of things. And then up to about 2000, there was sort of a decade there where we're doing all sorts of stuff. We're trying to find out how can we do this in a low-cost way? How can we do this more effectively? This is sort of a whole bunch of ideas about, we're doing all sorts of lab testing and field testing. You'll recognize some of the people in these pictures. There's even a younger version of me in there. And we also started to think about when is it really hard to measure stuff? And the toilet is the most important picture here, which you probably all knew that because you were ahead of me. How do you get a regular flow hood on that grill to measure I mean, what? And guess what? Loads of houses do that, right? We'll get a bit more into that. And just to give you a flavor, for those of you who've ever worked with standardized test methods for calibrating stuff, you'll have seen crazy stuff like this. We have very, very precise engineering drawings. You build a thing in a test lab, and we can very, very carefully get the true flow and compare our flow measurement devices to it. Here's another little test setup. Actually, there's two here. The thing on the floor is just, some nice straight bits of pipe to calibrate for measuring one flow on one duct. The thing that's sort of up in the air on the platform is sort of a fake house system where we actually built a duct system in a very strategic way inside a warehouse that we actually connected to a fake house where we could look at what happens if you've got a big distribution system. That's more for heating and cooling than for ventilating, but still it's how we evaluated what happens if you've got different grills of different sizes with different airflows, what happens if you've got branches that are close together and far apart, and all that sort of nonsense. And then our industry is fantastic at not being standardized about anything, right? This is just a sample of things we tested in terms of air inlet and outlet terminals that you see either inside dwellings or stuck on the outside of dwellings. They're all over the place, directing flows in interesting directions. And it's not trivial to get everything right when you're measuring flows that have all these highly, highly directed flows, right? This is part of a long learning process about what works and what doesn't. It has to work for all these things, right? So I'm going to talk a little bit about what I might phrase alternative methods. And the two on the top are basically what turned into some flow meters that you can now get commercially available and look a little nicer. But it's effectively the same thing, which is if you cut some holes in something, you can make an airflow device. right? If you physically measure those hole sizes just with a ruler, it turns out it's pretty good. You have to have that good pressure sensor that I talked about. Okay, you have to have a really good way of measuring the pressure. And there's fiddly things that are very hard to see in these photographs, like if any of you are keen gardeners, you may have used something called soaker hose or soaker tubing, which is a porous bit of tube that you put in the ground, put water in one end, and it seeps out the full length of the tube. Turns out that is an awesome way to average pressures all the way around the perimeter of the inside of your garbage can, if you want to use your garbage can as an airflow measurement device. They totally work. But you don't have to do this because you can go buy these commercially, and they're not even expensive. But this was sort of where those things came from. There's a lot of goofing around with things like this, trying to find out would it work and would it not. The two pictures at the bottom are, of course, my personal favorite test method of all time because my background is mechanical engineering, and I'm a bit of a purist, which makes me a pain in the butt. But it means that if I want to know what the airflow rate is in cubic feet per minute, I want to measure cubic feet, I want to measure minutes. All these other things are some hand-wavy nonsense that is sort of related with a calibration. Who knows, really? But this is truly volumetric flow and time. And you know what? It kind of works. For supply grills, which is where the little blue bag is an example, it's actually pretty good. To do exhaust or returns in an HVAC system, you have to pre-inflate the blag, and here's some of our old-time friends doing it like that. I think that's really, really difficult to do. Maybe slightly less practical, and of course, no manufacturer specifies an uncertainty that you can compare to what it says in your design drawings or your passive house requirements, right? There is nothing to refer to. So although these things might work, to legitimize these is complicated. You need somebody to go out and actually manufacture a thing and certify it. And certainly for like the hole in a box, that has been done. But as far as I know, you can't go out and get a calibrated bag yet. But it's still a really, really good test method. And I want to point out that it's not just me and some goofy researchers saying this, right? Serious people like the Canada Mortgage and Housing Corporation were telling you how to do this back in the early 2000s, and sending this out to people to go, this is the thing to do. Oh, come on. Oh dear. And in fact, the computer likes this method so much. And here's an amazingly grainy old video to prove that in the 2000s you could actually take videos. I don't even know if this embedded video is going to work on this computer, and it's going to not. But if it worked, what would happen is you'd see this French student put the plastic bag down, the air blows in it. The thing that really makes it work is having a little cardboard shutter or something, sort of super duper idea. It doesn't matter. You've all seen it, I assume. Have you all seen this happen? Actually, you don't have to. Just go home and try it out. Just go home and try it out. All right, moving on. We do a lot of testing in homes, and of course, I could never do this in the modern era of my IRB, who approves the fact that we can actually even get people's electric bills, would never allow me to use a child in an experiment. But we allowed children to try this test method out and their aging grandparents, and they were surprisingly repeatable. But anyway, I digress. I try to sort of summarize a bunch of these, all these ideas together in a table here. I know this is boring numbers that we, who cares? But the point is that out of all of this nonsense, we learned that if you do something like a powered hood, something that has pressure compensation and a really well-calibrated flow meter in it, my goodness, almost all the time, you're within about 10% or 5 CFM. We tested a few vane anemometers, and I'm not picking on Testo. That's just the one I had for these data. Not so good. Super, super sensitive to the fact that not all grills are equal, right? A lot of passive, and then the passive device is the nice manufacturer box with a hole in it. It's actually, for exhaust, pretty good, but we don't use it for supplies. And then you can go and buy bolometers from Alnor. Many other manufacturers exist, but they all perform the same. And in fact, Alnor, in my experience of field lab testing, is one of the best, in fact. There are some brands I won't mention which they can't even calibrate at the factory. They are so far out to lunch, it's not even funny. But you can see that some of the time they're okay, but the number 2 there, it was so sensitive to placement over the grill and the grill shape, for supplies, we couldn't get any of our measurements within 10% of 5 CFM. So caveat emptor, right? And of course, there is no way when you purchase one of these devices to know that information, right? That's not, because these are all calibrated with a single straight piece of duct and an inline fan and flow meter. There's no crazy grill on the end of it. It's all very uniform flow. The flow is designed to uniformly fill the entire entry of it. And if you have that, fine. But in homes, it doesn't happen. And I have a ton of these. I'm going to go through these pretty quickly. This is just to prove we actually did stuff, I guess, is that, you know, we went out to people's homes, we measured tons of airflows, and I sort of shaded the area because we're supposed to be talking about ventilation today, right? And where ventilation airflows might be. The dashed lines are plus or minus 5, 10, and 15%, right? And, you know, these are a bunch of hoods that are like, those passive hoods, man, they're going to have big errors, right? This sort of flops around all over the place. But when I use one of these active hoods, they're really, really close. They always get within that 5% pretty much all the time. So that was out in actual homes, which is sort of a, you know, the more practical test. If we do a lab test where we can make things a little more extreme and do things like picking different grills and centering not quite well, you can have really horrible errors with passive hoods, and active hoods have small errors. There's a continuing theme here that I think is probably pretty straightforward. I have lots more of these. We're just going to skip them because the answer is that the passive hoods can have these big problems. Not always, but you know, how do you decide if it's going to work on this grill or not that grill, or with this system or with that system, with a branch or without a branch? There is like no rating that tells you if this thing works or not. And I want to emphasize, we did not do this alone. I've stolen these results from some friends of mine at the Energy Conservatory, from Steve Rogers, but me, Steve, other people have done this too, and we all kind of agree. So I just wanted to emphasize this isn't just LBNL doing its foolish West Coast nonsense. Lots of people measured results that are all over the place. These are just some results I stole from Steve, but the results are kind of the same. What they found at the Energy Conservatory was that if you use active hoods, they also found one single device that used had a built-in hot wire system that actually wasn't very sensitive to placement over grills and things like that. That worked pretty well. So that's all about getting airflow right. I would say one of the biggest challenges we've had in field testing, like actually going to people's homes and trying stuff out from an R&D perspective, or when I talk to contractors who are trying to do this, is can I even access all the grills? And again, I'm talking generally about all of HVAC in residential, but this applies to your ventilation inlets and outlets also. So, you know, when you put that supply grill up in the ceiling of a new build with high ceilings, and it's 2 stories in your great room, some poor chump has to climb that ladder and try and measure that without falling off. That's no fun, right? You want to verify that airflow? It is. I'm going to show you worse ones, by the way. Or they get stuck up in the ceiling where the peak comes together, or you know, 1,001 places where you can't put an airflow measurement device. That's almost the only thing that works on a lot of these restricted space things, actually, weirdly, is the bag inflation, because you can put a little wire around it and make it any shape you want. It might be the only way you can do it, right? But when we talk about good building design, and I know all of you are passive house experts and your designs are fantastic, you always place the air inlets and outlets where we can easily verify the airflow, correct? It always happens. Because if I can't put a measurement device on it, I cannot measure it. And if I can't reach it easily, I cannot maintain it. This is particularly true if you're thinking about exhaust vents, which, you know, they fill it with fluff. We've all seen these pictures, right? When is an exhaust not an exhaust? Well, you wait 2 years, right? If either the occupants in an occupant-owned building or the building management in a rented place, if there's no access to these things, they can't be cleaned and maintained, and they won't work. We can pretty much guarantee. You just have to wait. If you want failure, you just wait. One of my, yeah, right. But this is reality. So you all heard of a CFIS ventilation system. This is where it's basically a hole in a return. You have a duct from outside, goes into the return side of your central forced air system that sucks air in, blows it to out of the house. Sounds great, right? Now I have to verify that ventilation airflow. The only place I can access is this external air inlet. Well, good luck, right? Does that look like a repeatable, easy to measure thing to do? We've designed in massive flaws, right? We've designed in the inability to find out if the system is working. I mean, who's going to go up there to check the air inlet isn't plugged up 3 years from now? You all know the answer. It's exactly nobody. That's ventilation system is only a ventilation system for a little while. I've got a lot of this sort of ventilation system horror show stuff, right? So we talk about duct traverses. How are you going to do it where there's 17 elbows, or a scrunched up piece of flex duct? It's not happening. A lot of these measurement techniques are not available. Then I've got that other air inlet there. It's hard to see in this picture. It was a long way up. I did not want to climb a ladder at a very, very steep angle to try and verify that air inflow. And I don't want to ask any of my contractor buddies to do it either. That's not safe. We've all done unsafe things in our lives. Come on. We joke, but it's serious, right? If we are serious about, are we getting airflows right in buildings, whether it's for ventilation, heating, cooling, you name it, if we do foolish things of where the holes are that we care about the holes, then we're making our lives very, very difficult. And I'm not saying it's impossible. I'm just saying it can be unsafe, and we're not helping ourselves when we do it. And so we'll talk a lot about can we get within 15% using this particular device that you just purchased for many thousands of dollars. But if you cannot access where the airflow is, I pretty much guarantee you won't measure it. And just to finish up here, these are some great pictures from inside attics. Again, these are mostly supply systems in this picture. These are supply ventilation systems, all effectively completely inaccessible to any human being. And this is on and my most recent experience doing field work was in Fresno, California in the middle of the summer. It's only 160 Fahrenheit in the attic, and it's full of loose fill glass fiber insulation. I'm telling you, I didn't want to go measure that. And it's foolish to assume that anyone else ever will either, right? That's no fun. No fun. And then one of the things we've talked about a lot in the world of ventilation is not just ventilating generally, but to extract well from kitchens and bathrooms to remove things like moisture, contaminants, odors, the stuff you don't want. You have to move so little air to do it compared with whole house ventilation if you ventilate at source. This is more about source control, ventilated kitchens and bathrooms. We should all do it, particularly in passive houses, right? Because you want to minimize the heating or cooling penalty of all the air you move. So exhausting here at high concentration is a great thing to do. Kind of challenging to measure though. And I guess we all get used to building our custom cardboard boxes for every single range hood we've got to measure, but that's a bunch of no joy. You can go on the outside the buildings, which is what the other picture is here. And frankly, the picture on the left here, I believe, is actually an exhaust from either a kitchen or a bathroom, trying to measure on the outside. We're not helping ourselves, right? So the point I'm making is it's not good enough to have excellent devices. You have to find ways to use them. And so what do I use when I'm doing experiments at LBL? We like a powered flow hood, although the picture of the one there, you can't have that anymore. Who knows? We like these simplified devices also. And you know what? Sometimes you just have to do custom things, which is okay from an R&D perspective, but terrible for general practice, I would argue. Right? You might say, well, I'm doing a multifamily thing. There's 40 kitchens. They've all got the same range hood. I only have to build the cardboard box once. But, it's still no fun, right? So what are the key issues when we're measuring airflows in buildings? Whether we're ventilating or measuring our heating and cooling system. There's problems with it. If you put something that's got flow resistance in it, which is the traditional way of doing it, you're going to get less flow, particularly on branch systems and so on. There are ways about that with pressure compensated devices, active flow hoods, and so on. The bag is kind of low flow resistance, but I realize it's hard for people to take seriously, even though it is a fundamental measurement. But I think if somebody sold branded bags, we could get along with, your logo here. You could get some ways to that, right? There's a lot of sensitivity for residential systems because our air inlets and outlets tend to be small, much smaller than the average entrance to a traditional flow hood that was developed more for commercial systems, generates lots of problems. And just generally measuring small airflows, a lot of the devices you can get commercially were never designed for that, they were never calibrated for that, and they won't work well for that. And a lot of the airflows we're talking about, if you were talking about multifamily ventilation rates, those are small numbers. Then we get things like, if you want to do pitot-tube traverses or inline devices, we almost never have enough straight duct in the residential applications. Access is important too, so if you learn anything today, when you design your next building, please allow me as a researcher and your colleagues in the construction industry and the verification industry to actually access what you have installed. And who knows, maybe they'll even maintain it and clean it, but no promises on that, right? Tomorrow, I'm going to talk a little bit more about some very specific devices that offer some interesting challenges about systems that might, interact with the airflow device you're using, for example. But we'll skip over that for now. This is kind of a summary of what I've been yammering on about here, what works and what doesn't. And I'm going to finish up here being very specific about RESNET 380, which is sort of become the de facto sort of national standard for how do you measure these sort of things. And we have things that you can use for air inlets and air outlets, not always the same, ways you can measure in-duct airflow. And I would say that the challenge with any standard like this is it represents the state of the art when it was initially drafted, and then things change. Or there was a particular kind of thing we wanted to measure that we weren't thinking about back then. And so again, this is something we're probably going to talk a little bit more about tomorrow, measuring some specifics of specific types of ventilation systems, is that what needs to happen is that these things need to get updated. If there's a new measurement device, when we have very specific standards that say do A, B, and C, and this device does not do A, B, and C, you end up with a device that's a really good airflow meter, but you can't use it because the standardized test methods don't mention it. But that's fixable, right? These test methods are not written in stone. You can always try and change them. But this is sort of the state of the nation in terms of what RESNET 380 says to do. There's a lot more details on this, obviously. They sort of clearly outline all the step-by-step procedures and the requirements that you need to have and so on. And I've got sort of like one more thing, which is, I sort of touched on this in this idea of maintenance, and something I want you all to think about. It's sort of another little, because I've got you all in the room, right? I can talk to you about what I think some of the issues are beyond simply measuring airflows and designing things properly. If you have supply air to a building and you're going to put a filter in that supply air, and you should, by the way, because the number one indoor contaminant for health is particles. The vast majority come from outdoors, by the way, in a residential application. So you should filter that air. Pardon me. You should be very careful about how you design where these filters are. Firstly, they've got to be easy to access. They never are, I know, but please try. They should fit properly, and they almost never do. And why is this? Is this because the original filter fit well, 2 years later they swap it out for one that doesn't fit well? Happens all the time. Don't know how to fix that, but this is all part of, this is sort of beyond the design. This is about building maintenance and building operations, right? We need to think about these things. Or we just use terrible filters, like the filter on the left there. That does absolutely nothing for air quality. It might stop very large things plugging up the fan motor and the blower, which, okay, that's reasonable. But that's not good enough to meet standards like 62.2. 62.2 currently has these sort of minimum filtration requirements that are better than that, but not a lot better. But I will tell you that is in flux, and it would not surprise me if we end up with much, much more stringent filtration requirements pretty soon. Not just in 62.2, but more broadly. And that's because we live a crisis, right? And the crises we've had recently to get us thinking about filtration, things like wildfires and airborne viruses, has sort of changed our outlook here a little bit. And so I want you to incorporate filtration. I want the filters to be accessible. And I want you to consider them in your design for airflows. Okay. I'll stop there. you can contact me there, but you have me here in the room. And we have I've got 25 minutes for some Q&A. I've got lots more slides, but we don't need them, right? Hopefully I've raised enough issues that we can have a little chit chat, and I'll try and answer your questions.
Thank you so much. All right, we've got our mic here, which I can bring out to you. We'll take questions from here and online. So, who wants to start us off?
If you don't, I'll ask questions of you, because I have questions.
He'll do it.
Put you on the spot.
Ken.
All right. Thank you, Dr. Walker. This has been interesting and exciting. So we are struggling to measure airflows. How much airflow do we need?
If you're talking, pardon me, sorry. If you're talking about minimum airflows, the ASHRAE standard is your starting point, right? And it's sort of, for general dwelling ventilation and exhaust from kitchens and bathrooms, it sort of lays out what those airflows need to be. That's sort of a pretty straightforward answer. But the more complex answer might be, yeah, but that's a minimum. You can't go below that. That's absolutely the worst we will let you do. It's like most building codes that you're all familiar with are generally, you can always do better, right? The building code just says you can't go below this. It's sort of a minimum performance. So that's what the ASHRAE standards are for. They're about a minimum performance. You can always do better. And the one thing that always comes up is, should we design ventilation systems where we install a system that actually allows more airflow? What if you're having a giant party or something and it gets, you want to just for an evening have more airflow? Or we look at low-income multifamily housing, or just housing in general, where a two-bedroom home has 8 people in it and they're home cooking all day. They need a lot more than that minimum. And wouldn't it be good if we'd installed a system that they could turn up? So the minimums are what we have in 62.2. Is it the right number depends on, unfortunately, who's occupying it, how many, what are they doing? There's a lot of questions about that. And really, as a designer, the only thing you can do is give people the option, give people the capacity to change their ventilation system. There are also caveats about, what if I clean the air, right? Do I need to move that much air? And currently in 62.2, there is a whole calculation procedure that says if you do a really good job of filtering the air, you can in fact reduce the total airflow requirement because you've removed those particle contaminants that are so important from a health perspective. So, sorry, that was a long answer to what seemed like a simple question, but there isn't an answer, I guess is my point. There isn't one number works all the time for all occupancies and so on. Because it's simply the truth. There isn't one answer. It depends. If you know there's a lot of occupants, you should add more airflow. But the sort of the baseline, the minimum, is what the ASHRAE standard talks about. Was that helpful, or did that all make sense? Hopefully.
It's a good starting point.
Well, if you have a follow-up question, you should ask it. Please.
So I guess the follow-up would be that it's great we have an airflow rate that we need to provide as a minimum.
Yeah.
And that's based on assumptions about occupant behavior and number of occupants. It's based on assumptions that folks are home. It's based on assumptions of the off-gassing of the materials in the space. And these are a lot of things that we don't know. Maybe we can measure to some extent, but is there something more direct? Because I feel like the airflow rate is a rather indirect way of getting what we're trying to do with ventilation.
Sure. That's a great can of worms to open, so let's cut the lid off, shall we? Sure. If you could measure everything you were concerned about, you could then have some system that said, so long as I'm keeping various contaminants below certain levels, including humidity, for example, so long as no one was complaining about odor or stuffiness because they carried around some device that they could click a button that reported on that, Sure, we could have variable ventilation rates all the time. The challenge is but that's really an intractable answer, right? That's not helpful to you because we just don't have a way to measure everything. I'll come back to that in a moment about what is everything. Turns out everything isn't everything. The biggest challenge is probably the response of people in the space. People are not responding necessarily to things that are of a health consequence. Primarily it's particles, but you can consider formaldehyde some of the key contaminants of concern. People respond to things like odor, and it's not always a conscious reaction, right? People respond subconsciously, but when you ask them, is the air stuffy, they'll say yes, but it's not particularly because they're smelling something. They will just tell you it's stuffy. So I think maybe what you're getting at is the genesis of the ventilation standards at ASHRAE and pretty much worldwide were based on odor panel testing, right? Where it was human response to things in the air, and we figured out how much do you have to ventilate so that not everybody, but most people think it's okay. So ventilation standards are not about zero risk. They're about acceptable indoor air quality. They're based on what people say they think and feel about the air. That was the genesis of them. And why have the rates changed? Because of other things that since those genesis times, right? We've got a lot better at measuring things in homes from an R&D perspective, right? And we've got a lot better understanding the health consequences by working with people in public health. And so the thing I wanted to get back to is I don't think we have to measure everything from a contaminant point of view, getting away from, how do you get input from people to change ventilation rate in a building is super, super challenging, right? But put that to one side. We kind of do know what the key contaminants of concern are from a health perspective. In other words, what's common in buildings at concentrations that we know have health impacts. And the number one thing is going to be particles, almost by an order of magnitude, right? On average over a population, not for an individual building, by the way. We'll get back to that. Then it's things like formaldehyde, oxides of nitrogen, more so if you have combustion indoors, less so if you don't, right? And radon, again, very much depends on where you are and where you built the building for radon and what sort of a foundation it has. And radon we often subtract that out. We don't try and deal with radon with a ventilation system. We use other systems to control radon that are part of building design. And I think that is the right approach, by the way. We should not try and just ventilate radon away. We should use things like subslab depressurization for that, right? So we do have some things that are controlled in that way. Similarly, emissions from things in the space. I would point at carpet if we had some, but we don't. Or furnishings. They've actually gone down quite a bit in recent years. Due to some pretty good regulation that said we just will not allow very high emitting products in buildings, turns out that worked. And if we look at formaldehyde concentrations from 20, 25 years ago in homes, compare them to now, they've gone down a lot because we are emitting at a third of the rate we used to emit at. So some of the issues, like radon and formaldehyde, were dealt with from a source perspective. We didn't try and deal with them with ventilation, right? And so all of these, this is sort of like the giant soup of things we have to consider if we want to get away from something that's as simple as here's the minimum we'll allow. If we want to get into controlling ventilation to maintain things. And some of that is happening. I will say that we're currently right now at ASHRAE 62.2 working on an approach where if you measure key contaminants and you can show your ventilation system keeps them below certain levels, we can call that compliant. There's going to be a floor that we won't go below, obviously. There'll be like a minimum that's lower than the current minimum, right? An absolute minimum. But the gap between that minimum and the current minimum will be adjustable. So if you've put in like a super duper ventilation system that removes all the particles, if you're not doing any indoor combustion to emit oxides of nitrogen, if you specify low emitting building products to really control formaldehyde, and then you measure them well, in the future the standard is going to say, well, then you don't need so much ventilation. So these things are happening. I would say. They're in flux. There's a proposal that the 62.2 committee is currently working on. And, there's pluses and minuses. The key thing, I think, has got to do with actually sensing stuff. Like, can you measure things well enough to be sure that for 20 years I can measure PM properly so that I can justify putting in a lower ventilation rate? Those are debatable, and I don't have a good answer for you. But you can do the same thing with other contaminants too. Again, sorry, long-winded answer is yes, there are other alternatives. Are they currently available to you? A little bit, yes, but not quite. But certainly for removing particles, 62.2 will, if you do that well, you can have a lower ventilation rate. But it doesn't absolve you of exhausting from kitchens and bathrooms.
We're going to have the other questions and answers be shorter-winded. We've got one here, then we're going to go to some online as well. Unless yours was answered already.
Well, it was just kind of bouncing off of Ken's first question. I'm a home energy rater, and 9 out of 10 top jobs, clients only want what's required by code. Mm-hmm. And even if the code says it, if the building inspector is not asking for it, it kind of gets forgotten about. So how do we educate the building inspectors to actually ask for these things?
It's been a problem for basically forever for things related to ventilation and air quality. Because if the heating goes off in a building in the winter, there's a pretty immediate feedback loop that says we should probably address that, right? But most of the time, if we don't have a building with some terrible moisture problems or something, right? If we're just talking about we're ventilating to remove the contaminants and it gets turned off for a week, who would know? Seriously, right? Unless there's some like odor problems or moisture, because it's things people do not detect or respond to. And so it's something that people have shrugged their shoulders about, right? And that's been true for a long, long time. I think that has changed a little bit. The two topics I mentioned a few minutes ago have increased broadly public awareness. I think it hasn't actually penetrated through to ASHRAEs, by the way. But if you talk to human beings who live in homes, which we occasionally do through survey instruments and so on, they really do care about things like wildfires. They really do care about infectious diseases and so on. And issues relating to, is the air I'm breathing, quote unquote, clean? I'm using a term that, somebody in your family might say, not what us amazing experts might say, right? But they talk about clean air, right? People want clean air. They want a healthy home. People with asthmatic children do not want their children to have asthma attacks. They really genuinely don't, right? And so that's how we have to start framing these conversations. And if you're talking to people from AHJs, that's how I think you frame it. Is in you want to protect the health and safety of children, and that's what this device is for. And that sounds like I'm trying to make an emotional argument rather than a scientific one, and that's partially true. But we're talking about hearts and minds here, right? You're right. You could just wave a paper at an HJ and say, "Oh, just read this." You will have no response. But if you frame it in terms of, in this community, I don't want anybody complaining about children having asthma attacks, and so we need to make sure we're ventilating right. That is how you frame it. If you want enforcement to work, you have to give people a reason for it that they can connect to, right? And abstract research papers is not it, but framing it from that public health perspective of, I want the families living in my homes that I've designed and built to have a healthy environment and not have their kids have to go to emergency because they're having an asthma attack. Therefore, we have to do these things, whether it's air cleaning or ventilation, specifying low emission products, whatever air quality thing you're doing, that's how you have to express it, right? In terms of things that people think are important. And so, manipulate them emotionally and talk about, don't you want children to be healthy? How much do you hate children? This is how we control people. We're laughing, but we all know it's true, right? That's how you change hearts and minds, right? And of course, I'm going to advocate that, and by the way, we'll back up those statements with really, really rigorous science and research where we measure lots and lots of things and we take children to see a physician and make sure actually this is happening. That's all happened in the background, right? That, you know, if somebody asks for proof, we can give you the proof. But in terms of hearts and minds, we have to talk about it in these terms. Like, we're providing a healthy environment for the people we're designing and building our homes for. That's our job. We take it very seriously, and we want these people to be healthy and happy. That's what I would say.
Okay, just for time management, raise your hand if you have a question in the room, because you got a bunch online.
No.
Okay,
We have one more.
Carla and James. All right, we're going to take 2 online, then we're going to get to these 2 ones, and we're going to try and get these rapid fire so we can.
Okay, I'll give shorter answers if that's helpful.
Shorter answers, because we just did 20 minutes and 2 questions. We got like
There we-
10 more questions, so we're going to pop them off.
I've got nowhere to go. So
Question.
I'm trapped.
Regarding car dampers, A, can they be accurately balanced, though tough with low flow CFM, so we're talking about multifamily, and do you think that they are more accurate or efficient when compared to standard grills?
Okay, so I'll take the last bit of that question first, if I may. So, if you're just using a regular damper in the duct, the airflow is going to be super sensitive to all the other things that happen in the duct, and the whole purpose of a car damper is to reduce that sensitivity by and large. This is true, right? So, if you're trying to have an airflow that is less sensitive to how the ducts got designed, or if you've got a multifamily application where there's many, many units attached to one vertical shaft, then that's going to make it much easier to be at least close to the airflow that you want, rather than manually adjusting adjustable dampers, because that is just a nightmare. For any of you who've tried it, I think you probably agree, it's not trivial and it's massively painful, right? So let's avoid that pain. And I think the first part of the question was more about if I adjust it to the 25 CFM number, is it really 25? Is that a reasonable paraphrase of the first part of the question, maybe? So I have not myself done a lot of verification, but I know some people have. And I think it's pretty good, but not always perfect. And so we would have to debate how much imperfection do we allow, right? And again, I want to get back to, Ken, I think you asked me about a minimum, right? So we've been through this with a whole bunch of things related to buildings in terms of insulation levels, I should say things that get measured, like airtightness, right? If your target's 3 ACH 50 in the code, I know it's passive house, so we're not doing that, but if it was, right, what we find is builders meet it all the time. So on average, they're at 2.7 or something like that. You can do the same thing with airflows. Like if you need to get 30, set everything at 32. That way, if you're out by 10%, you're still going to get that minimum. That's what I would advise, is build that into your design process, or your, maybe not the design process, but into your construction process. Next question.
Great, so this is a couple comments from Graham Wright, who was staff scientist at FIAS. I don't know if you guys know each other, but he's commenting that ASHRAE 241 outdoor air path wants 30 CFM per P. I'm not sure what the P is.
Per person, I think that would be.
Okay. And then he thinks that's for dwelling units. 241 is infectious aerosol control, and he's curious about tracer gas approaches regarding those inaccessible tests. So do you have comments about any of that?
Sure. There are tracer gas approaches you could use, but they're incredibly challenging. And I think for those inaccessible ducts, even then it's going to be very, very difficult to do, because you still need to access the duct to inject the tracer gas, then find somewhere else downstream to sample it. It can be done, but it's still very, very hard, frankly, for those inaccessible ones. As for 241, so for those of you that don't know, 241 was a standard ASHRAE developed in response to the COVID crisis, and it's a tiny, tiny residential section. It's almost non-existent, right? But it does have requirements for how much flow per person, and it is more air than you would have currently in the minimum standards, and that's because we want to dilute the contaminants in space, in this case, an infectious aerosol more. Not a surprise. There's a whole new version of 241 that's going to come out shortly. We're in the process of finishing that right now. But I don't think those numbers are going to change very much. And effectively, the short of it is, because we have other questions, is yes, the airflow requirements are greater if you're in infectious aerosol control mode than if you're not. And that goes back to my issue of, should we be building that into systems? Should there be a button you push to go to a higher airflow? Just build it in. Don't always shoot for the minimum. Because if you shoot for the minimum, I think the question is, how can I meet the requirements of this other standard? And the answer is you probably can't.
All right, we're going to go to Carla and then to James here.
Thank you. Carla Butterfield with Stephen Winter Associates. Design to the minimum, but put a little buffer in there. Love that. We're doing that as verifiers.
Mm-hmm.
And then we run up against our energy model, especially when we're getting through passive house with the ERI path. So little buffer. We want to be realistic, what we know we're going to test on site versus what we're putting in the energy model, so we don't fail later. And again, like, there's no buffer there. You know, very, very little wiggle room for the ERI index, for the HERS index. So how are your establishments working with 380 to make sure they're quickly progressing as we change how we're measuring and what our reference home is doing in the modeling?
So that's probably 5 questions, I think, secretly, but okay. So in terms of what's happening in 380, 380 is basically what's we call a continuous maintenance thing, which is anyone at any time can go to the ASHRAE website. That'll lead to failure for RESNET. Go to the RESNET website, and you can put in a comment that says, I'm doing this in my practice for 380. I find that it works very well. I have some suggested language for you to change 380, and it will be considered and will, if it works, lead to a change. 380 is always open to change. You can put in your suggestions at any time, and they will be taken seriously by the committee. So I encourage you all to, sometimes solutions are about engagement, right? And the 380 process is very open, so please engage with that. Your other question was about if that extra 5 CFM is going to push me over an index that I'm trying to reach the target for, what am I to do? Probably I don't have a good answer to that. You're going to have to find those savings somewhere else. And ventilation is one of these funny things that we can do energy recovery, right? That helps a lot. Maybe you just pick a slightly higher performance ERV if that's what you've got, and you can get there, right? But if you're already using the best ERV in the world, and that 5 CFM pushes you over the limit, it's only be by a tiny amount. There must be something else you can do. Is my answer to that. It seems unlikely there would be something else. But the problem is it may be costly. But here we are, right? I can't stand here and advocate to say, it's okay just to take 25% off those flow rates. I have no basis to support that, right? What we do have is a basis to support the current rates, because we've measured homes that have those rates of airflow. We've measured the contaminants in those spaces. Turns out the rates we currently have are pretty good in most houses, right? It's not 100% perfect, but we don't have any evidence to say, it's okay to reduce those by 10% and everything will be fine. I can't say that.
Hi, Ian, James Peterson. Thanks for coming out, by the way. So I want to ask a sampling question, and I'll be as quick as I can, and I'll put it in a yes or no manner. So imagine a ventilation system for a multifamily, 100 units, and we have a DOAS unit, we have 2, so imagine 50 units. So we have a lot of openings. We have supplied each occupied space, bedrooms, living space, exhaust from bathrooms and kitchens. So 50 units served by 1 unit, we're going to have lots of openings, low flows, ununiform flow. So that's our design. And then in the construction process, the ducts are installed, they're pressure tested. It's a car damper system. They're pressure tested. We're able to spot check static pressure. We're able to make sure that we have static pressures exceeding the minimum at all points and not exceeding the maximum. So we do sampling in that way. And then we do traverses near the DOAS unit to get some gross sampling, maybe at branch ducts. So we have that. And then we have a powered flow hood. Well, before we do that, we're able to do some QC to confirm that there are carbon dampers at each outlet, each inlet, that they're in the right direction. Some QC.
Yeah.
So we've got that going for us. And then we have a powered flow hood. We have our bag inflation, which is a beautiful direct measure. I totally agree with that. I now understand why I like it so much.
Physics for the win. Yeah.
Must be my mechanical engineering roots, and it's the only direct measure. So we have the bag inflation. It can't be, it can't be. Granted, it can't be.
Get your question. What's your question?
Yeah.
I get that you've done a lot. Okay, but the question is.
Yeah. So we have that tool though as a spot check. We have the power flow hood as a spot check. We have the static pressure and the manufacturer's published data, which is third-party verified. We take all of that in a sampling way. What stones can you throw at that method for verifying the airflow of that system?
So normally I would say, you know what, just go to every unit and measure it. You know, life is, ironically, life is too short to try and debate these things with death. But I understand where you're coming from, right? Because in other aspects of verifying home performance, we have sampling procedures, right? And sometimes you measure, 1 in 7 or whatever, and if you fail, you have to start measuring more. And for the sort of systems you're talking about, you could maybe come up with a sampling scheme like that, right? Where, particularly when you've got large numbers of units on an individual system. But that's something you would have to, unfortunately, sort of debate with the HJ or whoever's doing the verification, right? And there are standardized ways to do it. And if you want to do it, but by standardized ways that where people have done the statistical analysis that says we do 1 in 7, and if one fails, you have to revert to this. If another fails, you have to revert to that. Those are sort of pre-established pathways we can use if we want to go down the sampling route. But that's, I think, from a 380 perspective, they're just telling you if you want to measure the flow, how do you do it? I think sampling is sort of beyond that, right? That's not real, because the 380 is about how do you measure, not how do you implement these measurements in a rating scheme. The second thing is slightly different. And so I think if you want to pursue this idea of maybe we could do sampling, it wouldn't happen in the 380, it maybe happen in other parts of the RESNET process, or whatever certification process you're using, to have a discussion about when can I sample, when can I not sample, what would a sampling environment look like? Because I think there's already established precedent that says that's acceptable to do, right? We already have situations where sampling is allowed, we know the circumstances well, and so I suggest we use the well-established procedures we have, but again, I don't think it's a topic for 380. I think it's a broader topic for the rating and verification schemes, whether it's RESNET or whatever environment you're working in. But it's certainly a viable technique for sure.
We still have a bunch of questions online. I wouldn't be surprised if we have questions here. I think we're going to keep going for a few more minutes, but for people who have to run, I just want to let you know that if you want CEUs, you should go to phmass.org/CEU. We're going to take our screenshot online now, so we'll verify your attendance now if you have to leave because we've reached our time. And if you're here, just make sure you sign in. And then we'll go for a few more minutes just to make sure we get the questions in, because I think we want to hear from the expert.
Should we do the online ones first? Because if people are in the room, I'm happy to stick around for as long as it takes. So
let's do a few online ones here. Raise your hand here if you still have questions in the room. We got one there. We also want to get people in the room. So look at a question here, and then we'll go to that gentleman.
At an ERV, would you consider total external static pressure measurements across both fans to be an acceptable substitute when you can't access the exterior vent termination in a taller multifamily building?
I think that depends entirely on the ERV you're using and what the manufacturer of that ERV says is an acceptable way to validate airflows. And in fact, there are ERVs and HRVs that come with pressure ports attached that basically have got built-in airflow monitoring, or it's been calibrated in some way. In which case, I would say absolutely. If the manufacturer of the product says, we've installed this airflow system, if you plug a manometer into these ports and it's in this range, We've calibrated it so we know the airflows are okay. Absolutely. Your challenge is that if the manufacturer of the device doesn't say this is an okay way to do it, or they don't publish the data that you would need to convert that pressure to an airflow, you're kind of stuck, right? So I think it's going to be very dependent on the specific device you're talking about testing. Again, there are definitely HRVs and ERVs out there that have got, let's call it calibration ports, whatever you want to call it, where you would measure pressure difference, right? In which case, okay, the manufacturer certified that if you do this, you can verify the airflow. But if they haven't, you really can't, right? I mean, if you ask the manufacturer of the device, if I connect here and measure this pressure, is everything fine? If they won't put in writing that it is fine, then it probably isn't, right? And so I know that's a very vague answer, but it's really dependent on the particular device you're testing and what the manufacturer says about those pressure ports.
So just a quick question on monitoring devices. Do you have any favorites that you're willing to endorse?
By monitoring, are you asking about things that sample contaminants in air, like PM or formaldehyde?
Yeah, things that we would be able to, because again, something a homeowner could have in their home that would say, now it's time to boost my ERV, or
Sure.
again, if they had that boost capability.
So there are quite a few what I'll call commercially available devices for homes. They're actually pretty good at some things. The thing we've got good at measuring at a relatively low cost is particles. Now, the caveat is you can't believe the absolute number, but the relative changes are pretty good, in fact. The reason for that is that they're calibrated with one particular size distribution of particles, and unless the emitting event matches that, you will not get the right answer. But they're really good at measuring relative concentrations, right? So things are going up or down, or it's twice what it was yesterday. They're actually pretty good at that, right? The biggest thing I'll say is the thing's been investigated a lot is wildfires versus regular particles. And they have very different size distributions. And we know that these low-cost devices don't get it perfectly for wildfires. But you know what? They still give you a great signal that says a bad thing is happening. So, and you should act, right? So PM we're pretty happy about. Temperature and relative humidity, again, they've been well developed for many years. The other contaminants get harder. We don't really have a great low-cost way to do oxides of nitrogen. And there are some ways to do formaldehyde, but they're not in these low-cost, things you can just buy for a couple of $100. But in terms of getting particles, temperature, humidity, they're actually pretty good. The other contaminant you might care about is carbon monoxide, but that's a story for another day. Maybe it isn't a story for another day. The alarms that you buy, you guys probably all know, are set to alarm at a relatively high rate because they're worried about all the quote-unquote false alarms at low rates. When the concentration isn't bad enough, you'll have an acute reaction and die, but the CO is still there. And the question is, when CO is there at a long time, do the chronic exposures that the current alarms allow you to be exposed to bad for you? The answer is probably yes. How much is less clear. So CO is a bit tricky. CO2 is one where you have to, some devices are good and some are not, right? And so what I will say about CO2 is if it's inferring CO2 from something else, and a lot of devices do this, then the CO2 is terrible to the point where it's actively bad information. It's so wrong. But if it actually is truly independently measuring CO2, usually with some sort of infrared absorption or something, then even the CO2 is pretty good. So you kind of have to provide a recommendation. I would say you have to read the fine print about what it is you're buying, particularly for CO2. But some things are still super challenging, and you're not going to find them in the low-cost monitor. But you know what? It doesn't mean they're bad. They're going to tell you a lot about the air quality in your home in terms of, if you're just doing it for households, should they do something? Yeah, fine. And there's a bunch of them, and they're all effectively work the same way. They're all about it. I wouldn't endorse one over another in particular, although, of course, as you may be hinting at the fact that that we've done a bunch of tests where we had like 20 of them in a rack, all side by side, exposed them, and found out what happened. And there are online databases where you can go and look this stuff up, like there's one in California, what is it called? It's the South Coast Air Quality Management District, have a huge database, publicly available, where they do really great thorough work, so you can really evaluate these things and look it up in an unbiased way that I'm actually not allowed to tell you, right? But they can and they will. It's the South Coast Air Quality Management District. And they even did the things where they had multiple devices, so they tested interrepeatability between devices. So if you and I buy the same thing, do we get the same answer?
Oh.
They looked at that too.
Okay, we're going to go one last question, then that's going to be it. We only have time for that.
One more, okay.
Opinions on resources for designing ducts for ERVs. I don't know if the air gets to where it should. Shouldn't there be velocity mixing at the register?
Okay, that's sort of two separate questions. In terms of I think there are standardized ways of duct designs to get the air to where it should. You know, longer ducts should be larger diameter if you want the same airflow and things like that. It's super challenging sometimes to do that, given that we have a limited range of duct sizes and terminals and so on. But I think there are standardized ways to do it. The other question is interesting, which is in some ways more of a comfort question about throw from grills and registers. Like, you don't want outside air being blown on you. You might be uncomfortable. So things like placement of inlets and outlets. I complained at great length about placement so we could measure it. It's also important to place things so you do not annoy the occupants. And so things like register throw and knowing where to put them high or low, and when you put a grill on it, do you have vanes that, you know, there are ways to like direct flows across solid surfaces, often ceilings, right? So you can make smart decisions about the grills that you use that will help you to stop complaints from people. And, you know, the short answer is you've got to spend like an extra $5 to get a good one. Just do it. And this is true not just for ventilation, but for heating and cooling too. There are really good products out there, and the incremental cost is really, really small when you think about the total cost of building a building. You know, maybe it's, you know, $30 per apartment. I mean, nobody even knows about that amount of money, right? It's in the noise. Buy the good grills. They're out there. No, I mean, it's seriously, right? This is all about, we've talked a lot about product selection. We talked about product selection a moment ago about air quality monitors. It's true for all the bits of hardware we're talking about, but this is an area where for effectively a very small incremental cost, you can actually do something.
That's a terrific message to end on. We have a round of applause for Dr. Iain Walker.
Thank you.